Hey guys, the objective of this video is to discuss 3D consolidation against 1D consolidation and to look at an undrained case. So we're going to look at all the undrained formulas. And in the next video we're going to be looking at the drained formula. So this video is just the undrained. So in the past we've been looking at 1D consolidation. Every single thing we've done, whether it be consolidation, settlement, all those formulas are based on the assumption that we're looking at one dimension, so that our consolidation or settlement is only occurring in 1D, and we've been looking at that being the depth of our soil profile. But in reality it happens in 3D, so we need to now develop criteria for stresses and strains in 3 dimensions, which is going to allow us to calculate settlements and consolidations in 3D, which is more accurate than 1D. So we're doing the same thing. We're finding at the end of the day we're going to be finding a settlement or a consolidation, except it's now in 3D, so we have a different criteria. So this can happen over a drained or undrained sample. So if we first look at a drained sample, so this is, we'll do undrained, and this sample is drained. So what that means is, we have, as we know, solid particles, solid soil particles, we have water, and we'll have pockets of air, and we'll apply a load. Now this load is felt all by the water, which means that we get a build-up of excess pore water pressure. Okay, so we get an excess of pore water pressure because our sample is undrained. If it's drained, that means that the pore water pressures are free to escape. So there might be a gap in the soil, a gap in our sample, which allows the excess pore water pressures to escape. We still have pore water pressure, but we no longer have excess pore water pressure. So we say that this sample is drained. In this video we're just going to be looking at the undrained formulas. In the next video I'll be doing the drained. So we can use formulas in 2 ways. There's 2 methods of finding the strain for undrained samples. We can either do it through the total stress method or through the effective stress method. Both answers will give you the same answer. Sorry, both methods will give you the same answer. So doing the total stress method first, we have the strain in the x direction equals the stress in the x direction, the change in stress, minus Poisson's ratio for the undrained value. So V subscript U denotes undrained, outside of strain in y direction, sorry, stress in y direction plus stress in z direction, and this is all over EU. So we can say that V subscript U is Poisson's ratio, and this is undrained, denoted by this subscript U, and EU is the elastic modulus, which is denoted, and this is also for undrained, which is denoted by E subscript U standing for undrained. We can then do the same thing in the y direction, so we're going to develop all 3 dimensions. This would be change in y, so I'm just replacing, so this was for x, that was x, this is for y, this is y, and the remainder goes in here, so that would be x and z, and this is all over EU, E subscript U, and as you could guess, the strain in the z direction would be change in sigma z plus V subscript U, change in x plus change in y, all over EU. So we would use, so in a question we'd be given say the undrained value of the elastic modulus and Poisson's ratio. We would then find the change in total stress. So because this is total stress, this is change in total stress. There's no dash there saying effective. So these are all total stresses, which is why it's a total stress analysis. And we have to apply the undrained value. So we would be given this change in total stress in the x, y, z direction. We'd be given the Poisson's ratio in E and Poisson's ratio of undrained and elastic modulus of undrained, and we can go and calculate all our strains in the x, y, and z direction. That's the first method, the total stress method. The second method we could do is doing the effective stress method. Both these methods will give you the same answer. We just need to do both. So we're doing the effective stress now. So you can see that all these values are in terms of total stress. So we need to put these in terms of effective stress, which means we need to find the change in pore water pressure. So what we're going to do is we're going to call this change in sigma m, which is the mean change in stress, And because we know, we discussed in the previous video, well not the previous video, some videos ago, that when we apply a load to an undrained sample, all the pressure is felt by the water and not the soil. So if we apply a stress, that is all felt by the pore water pressure. So the change in the mean stress will equal the change in the pore water stress. And we can find the mean stress by just averaging all the different stresses in the x, y, and z direction. And then what we can do so we'd be given those values, we could find our change in pore water pressure, our excess pore water pressure. We could then find our effective stress in each direction by going, the effective stress is equal to the total stress minus the pore water pressure. So that would be in the x direction, in the y direction, and in the z direction. So we could then find all our effective stresses. This change in u is just this change in u would find here, and these would obviously change based on our question, and we would find our effective stresses. We could then use those effective stresses to find our strains. So Ex, so the strain of x, would equal now the effective stress. So the difference is this is effective before it was total. So the effective stress minus V dash, I'm going to define that in a second, so that's not the same as the undrained value, Y dash plus Z dash, and this is all over E dash. So we now have different values of Poisson's ratio. So this is V dash, which is Poisson's ratio, but this is now the effective Poisson's ratio, the effective value, and E dash is still the elastic modulus, but this is now the effective elastic modulus, denoted by a dash. So we have VU and EU for undrained, where we use total stress analysis, and we have V dash and E dash, which is the effective Poisson's ratio, and Young's modulus, which you use for effective stress. At the end of the day, both these methods will give the same answer. I'm just going to write out quickly what this would be, as you can imagine. Minus V dash, it's X dash plus Y dash over E dash, and just quickly, we know that in the Z direction it would be change in sigma Z dash minus V dash, change in sigma X dash plus change in sigma Y dash over E dash. Okay, so just keep in mind, this might seem very confusing at the moment. We're going to do examples just to highlight what all this means, but just keep in mind at the moment you can answer an undrained question either through total stress, where you have to use these values, the undrained values, or by effective stress, where you have to use the effective values for V and E. The one last thing we need to do is just define this, that VU will always equal a half, and we can connect E dash to EU through this formula. EU equals 3 outside of E dash on 2 outside of 1 plus V dash. So if we're given E dash, we could find, and V dash, we could find EU, which means we could answer our question through both methods if we wanted to. The last thing we need to discuss is that the volumetric strain, which is EX, so this is just the total volume strain. So change in EX plus change in EY plus change in EZ, so this is the volume strain, is just a combination of all the dimensions, which makes sense. For undrained, so for our case, for undrained, this always equals 0, and this volume strain we can also write as 3 outside of 1 minus 2 V dash outside of sigma mean dash over E dash. This will also equal 0. Both methods will give you the same answer. Don't worry so much about the volumetric strain for undrained samples, because it always equals 0. But for drained samples, which we're going to see in the next video, it's not going to be 0, and you actually have to go find it. So it's been a very confusing video, I'm sure. All you need to remember is that we have just defined for undrained, we can find the strains using total stress or effective stress. Don't worry so much about all the formulas. We're just going to be using them in the next video when we do some examples. Anyway, guys, hope that helps.